Started with the next session, panel number 3, which is on advanced material. We have Professors Aparna Deshpande, Shauvik Dutta, Atikur Rahman, Professor Satish Ogle, and Prashanjit Ghosh, and Ashish Arora in absentia. So he'll.
I will become Ashish.
Yeah. Therefore, we have kept it. Yeah. So please get started. Thank you.
So I think first you.
So I can speak from here, right? Now it is available. Okay, good evening, good afternoon, whatever it is. So I will, I work in the area of advanced material. Our panel is for advanced materials. And for myself, I said, I will define what I consider as advanced materials. It is intelligently designed functional materials. That is my own definition for myself. Because this word is used so loosely that nobody understands what is advanced material. Okay, so advanced material actually is something which we design in a particular way to accentuate some of the property which is of interest to you in certain application. Okay, so it is engineering of different materials, trying to put them together and trying to make them unfold certain interesting properties which otherwise simple materials do not have. Okay, so that is how I define it, and my own particular area is in new energy and sustainability, which interests me. Actually, I've almost 30 years I've been working on all sorts of things which were closer to fundamental physics, like high temperature superconductivity, colossal magnetoresistance, multiferroics, spintronics, and so on. But from 2006 onwards, since I came back to Pune, I have decided to do, and it was a very conscious decision to do something which will be closer to applied physics, where the fruits of whatever we are doing can be looked into and felt on a shorter time scale than fundamental studies, which sometimes, after 50 years you see the fruits. Okay, so it is extremely important to do fundamental science, which actually influences different things, but applied science also can translate these fruits that you can see in your lifetime as an impact, and therefore the field of energy now excites me. So in energy, actually, this new energy is a term for clean and renewable energy. It is a common term which has come up, and the entire world is now looking forward to making a transition to, in our energy mix, whatever we use, we try to use more and more of clean energy so that the pollution will be all mitigated substantially, reduced, and so on and so forth. So there are different angles here: energy harvesting, energy storage, and energy conservation. The upper left slide captures that. I have indicated sun at the center because even wind comes from sun and all that. Okay, so other energies also are sun driven. Okay, now in harvesting also you have solar cells, then CO2 reduction to fuels, and so on. Okay, so that is the topmost slide. The other one is storage, where you talk about batteries and other things. And the third one is conservation. That is, you ask a question, whatever electricity you are using to achieve this particular illumination or whatever actions we are doing, can you do it in half the amount of energy? Okay, so how to conserve energy. Now, the materials at our hand are too many. In principle, you have nanotechnology. You see on the right side top, you see nanotechnology, which has come of age. There were almost 10 years when people were doing nanotechnology more as, excitement of making nanomaterials and testing their properties. But now people are able to make nanomaterials reproducibly so that you can use them in devices in real terms. And that is the field. In nanotechnology, one other thing which comes is two-dimensional, one-dimensional, zero-dimensional materials, because their quantum phenomena are accentuated in various ways and people are interested in using them. Then there is a new field which is coming up, which is quantum materials, because when you talk about electronic density of states, when you go to lower dimensions, you have a completely different nature of the electronic density of states that you get. And the whole thing started with a story of graphene, where you have this Dirac cone and other things. But many times a pure graphene is not much of use for electronic applications, because you need to produce a band gap which you can then manipulate into electronic devices. So manipulating materials is something important, and there in all energy devices you have interfaces. So if you take thin films and coatings, and sometimes these coatings are like 20 different materials put together. So now, one thing I am quite excited about this is that when you try to put materials together with diverse properties to generate new phenomena, like for example, there are many questions where you have two materials insulating while the interface is layer is superconducting. Okay, two materials non-magnetic, but interface is ferromagnetic. So interface is a new material. It's a very exciting opportunity and so on. So I think it is important. What I see here is that these materials are very complex and you try to put them together and you have to tame the complexity. This excites me because it is not easy to have 3 or 4 materials put together reproducibly so that a device can be brought in and it can be sold and it can go to in your pocket like a mobile. You know, you cannot believe how much complicated material science is because every device has to work very reproducibly and it is not very easy that every mobile you buy, you are not listening different songs when the same singer is singing, right? So this kind of reproducibility, even in lab, if you do 3 or 4 experiments, you have to see reproducibility, you put error bars and so on. So you have to imagine how complex it is. So taming complexity is something which excites me and that's what I'm doing. Thank you.
I would like to highlight that what Professor Ogle was saying, the summarize can be that advanced material need not be just a standalone material. It can be a material just beside it in the form of a heterostructure or an interface. And as Professor Ogle correctly pointed out, it can generate very novel properties when you study them. In my lab, we study actually electron hole pairs. When you generate an electron within a material, you leave behind a hole in the valence band. And immediately, because they are oppositely charged, they kind of attract each other like friends. And friends, just like friends, influence each other. Each exciton can also influence another excitons. So what we study in our lab is actually a collective property of excitons and try to see if we can actually use it for some quantum devices. And in our system, also because these excitons are electron hole pairs which can be described like a hydrogen atom like a model, I can say that I study atomic physics using a solid state structure. So that's what I do. And we would keep this short because we would like to field as much as questions from the audience. The next speaker, unfortunately, Ashish Arora, he is absent. And I am trying to be presenting his research work that he's setting up his lab on magneto-optical properties of 2D materials. There he tries to understand what happens to charged excitons. Basically, charged excitons are called tryons, where there is, apart from electron hole pair, when that dipole is bound to another charged electron and hole, these are tryons. And he tries to understand what happens to tryons if you confine them. He also tries to develop certain kind of a magneto-optical spectroscopy of these 2D excitons and tryon materials. He also is developing future plans. His future plans is strong exchange effect in 2D semiconductor heterojunctions. Again, that kind of tells you that that standalone material need not show you all novel properties. You really have to put two material together, just like one friend influence each another friend. So there we can get to see very different and novel properties emerge. And he also talks about these endless possibilities of the band structure of these 2D materials, where you not only have the bands but also have the valleys. And he plans to study room temperature based such kind of valleytronic devices in future. So next is, yeah, Prasenjit.
Okay, so so this is something which we do jointly with Professor Surjit Singh, who is not here currently. So one area of research is thermoelectric materials for energy harvesting. The idea is to convert heat energy to electricity to harvest the waste heat, which is generated, for example, in car exhaust or even in factories. And we use the Seebeck effect. The efficiency is given by, depends on the Seebeck coefficient, the conductivity, the electrical and thermal conductivity. Now, this is what is the scenario. So there is no upper limit on the efficiency that is given by the figure of merit ZT. So the efforts lie in the area is to design novel materials and try to push the ZT as high as possible. And, but this is easier said than done because most of these transport properties, they are interdependent and they depend in a reverse way. So for example, with carrier concentration, what happens is that the electrical conductivity increases, but the Seebeck coefficient decreases. So in the same material using the same technique, if I just dope more and more electrons, while I am pumping one property, it's detrimental for the other properties. So optimizing them is difficult. So what we are trying to focus in collaboration with Surjit's group and my group is trying to reduce the lattice thermal conductivity, which is relatively independent of the other transport properties. And we focus in two classes of materials. One is based on chalcogenides, which is for applications targeted towards low temperature thermoelectric applications, and for half-voiceless at high temperature. So apart from that, the broad area of research in my group lies in computational materials modeling. This in itself is a sub-area of research, and it's a highly interdisciplinary research. So what do we do here? So the aim, there are three aims. So in cosmology, for example, they try to reconstruct what happened in the future. Here, one of our main objective is to predict or design or say what will happen to a given material, say 10 years, 20 years from now on. So that's the primary objective. And in the process, we also understand experimental results. We understand experiments done in labs of Aparna or Shauvik or Professor Ogle or Atikur. And also sometimes there are certain questions for which it's really impossible or very difficult to do experiments. For example, in geophysicists, they are interested in what is the structure of the Earth's core. So then people know that it's made of iron, but in what phase they exist. For that to simulate in the lab, you need to go to few thousands of Kelvin, few thousands of gigapascal of pressure. So you cannot do those experiments in lab, and that's where also we can pitch in. And to do these things, what involves is study of different phenomena that span over several time scales, starting from picoseconds to decades, and length scales, starting from the atom, a few angstroms, nanometers to meter. So for example, in this graph, what is shown here is basically computational design of nuclear reactors. So what people are trying to understand is in fusion reactors to design a material which can last long. So basically what you need to do is you need to predict the stability of these materials for over decades. And one approach which we use is starting from the microscopic picture. So we start with the structure, we understand the structure, the electronic properties, and then how the system evolves in time. There are defects there, how the defects move into time. Then the defects, they grow, they form dislocations, and so on and so forth. So to address different time scales and length scales, there are different methods available. And in my group, we primarily focus in this domain. So we work on basically this ab initio electronic structure calculations, and using that, we look into different properties. So the general questions in the field, so in this field, you can work in two ways. You can invest your efforts to develop methods, computational methods, or you can invest your efforts to apply the existing methods. So in the area of method development, so one important thing is, so what we want to calculate these things from ab initio without any external input or without any parameterization. And the best way to do that is to solve the Schrodinger equation, but all of us know that we cannot do that. So there are different ways and different methods to bypass that problem to certain level of approximations, and density functional theory is one of that, is a primary workhorse in this field. but it has a problem. The problem lies in the description of the electron-electron correlation effects. So the basic idea of density functional theory is to write down all the interactions as a functional of density, and we don't know the form of the exchange and correlation functional. So if anyone can come up with the exact form, so that person can get the next Nobel Prize. Apart from that, computation of excited state properties, like for example, Shovik talked about excitons. So exciton electron hole interactions, then exciton-exciton interactions. That itself is quite challenging and computationally expensive. So right now, you can do for calculations, very accurate calculations for few systems, small system size consisting of a few atoms. But ideally, you would like to do this for large system size. And there you need to develop new algorithms to compute this. And the last thing, in my opinion, is there is a big gap in the length scale and time scales which we can access through our calculations compared to what experimentally is accessible. So for example, Professor Ogle talked about nanoparticles. So experimentally making a few atom nanoparticles or maybe 100 atoms, 20 atoms is very challenging and very difficult. So the experimental limit is a few nanometers where you have a few hundreds of atoms. While computationally reaching that limit, that itself is, it's very difficult. You can't do those calculations very easily. So this type of length scale gaps exist, and the idea is to come up again with methodologies to breach this gap. So in my group, I focus on 3 areas. So we work on the broad area of heterogeneous catalysis, where we are interested in studying important industrial chemical reactions and their reaction mechanisms, and to design novel catalysts which has a certain degree of selectivity and reactivity. As I also mentioned before, that we do thermoelectrics. And apart from that, we also study the effects of quantum fluctuations of the nuclei on the properties of materials. So this is relevant for biological systems, or when you, for example, design drug materials. So what happens is that we have heard about tunneling of electrons, but in these cases, the nuclei itself tunnel because, for example, the protons, they are very light mass, so they tunnel from one local minima to another local minima. And that changes drastically the properties of the materials. So this is all, and over the last few years, so machine learning has been also playing an important role in this area. So people have been using machine learning in 2 different ways. One is to come up with structure property relationships. And what we are doing is to develop interatomic potentials. So the idea is you develop models that describes the interactions between atoms, and with that you can study either the time evolution or whatever you are interested in. What you try to achieve here is, so this idea of developing interatomic potentials is already there in the area of classical molecular dynamics, but there it's very specific to a particular scientific question you are asking or a particular system. But here the idea is you develop it at a universal level. One potential works for everything. And also you want to have the accuracy at the level of a first principles or an ab initio calculation. And at the same time, you want to do the calculations quickly, at least at the speed of doing a classical simulation. So we are now investing some efforts in developing this type of machine learning interatomic potentials. So that's all from my side. Thank you.
Good evening, students and colleagues. I am in this group of advanced materials, but where my expertise or my expertise lies is in the investigation of the fundamental properties at the atomic scale of these advanced materials. The rate at which newer materials are introduced and then subsequently their applications get proposed also calls for a detailed investigation of their fundamental properties. And that's what we try to look at. And there are 2 verticals broadly for my lab. One is 2-dimensional materials, and the other one is strongly correlated materials. And the tool that we use is a scanning tunneling microscope. So we use the mechanism of tunneling to do the imaging of materials. And so this is exactly the direct proof of visualizing quantum mechanics in action is what happens in my lab. I'll just give you a brief idea of a few things that we have been recently doing. One of them being polymorphism in boron, where boron being electron deficient, it has been predicted that to possess different stable forms and unstable forms as well. And we were able to show that a couple of predicted forms, and like in the case of graphene, how experiments drove the field. First, graphene was discovered, exfoliated, so to speak, and then the field went forward. In case of boron, it's the exact opposite. There were theory calculations which drove the field, and we have looked at liquid phase exfoliated boron and found out that there are different phases of boron which people have not studied, people have not even looked at this scale, which is very important. See, when we talk about miniaturization of circuits and nanotechnology and so on, we really need to know what is happening at the scale of, at the nanoscale or at the scale of few atoms. Then there are newer materials. See, with the advent of graphene, also the field of transition metal dichalcogenides, all the older materials which were there came to the fore, and ZrTe2 is one such material where we realized that whatever results were reported, the oxidation of ZrTe2 is so rapid that it's almost impossible to take measurements on pristine ZrTe2. So we looked at oxidation of ZrTe2 and how, the oxidation starts with physisorption and then there is chemisorption, how the ZrTe2 evolves, and finally it goes from a very crystalline structure to an amorphous structure. And then, of course, we can think of applications of these kind of things for, say, oxygen sensors or for high-K dielectrics. Now, the area of strongly correlated materials, at the heart of this area is Phil Anderson's very famous quote, that more is different. And this is a very nice paper which I urge everybody, even peripherally interested in materials, should definitely read, where he says more is different, which means if you put together the individual parts, the collective properties need not necessarily be just the sum of the parts, but they are more, and there comes in the phrase of emergent properties, which again gets used everywhere. But the idea of emergence was given by Phil Anderson. And so we've looked at a couple of such materials, one being TISC2, where we see charge density waves, which is a collective behavior where the electrons and in some cases the lattice interacts and gives rise to modulations that we are able to see at the atomic scale in the STM images. Then we looked at Fe5-X GeT2, which is a very recent 2D metallic ferromagnet, and we saw that it shows very new orders of charge density waves. Why this happens is not very clear, and there are many ways to understand this kind of behavior in a magnetic material. And finally, the work that we are still continuing is Kagome superconductors. Now, these are exotic materials where you see superconductivity along with charge density wave patterns, and we can directly image these patterns with the STM and then get an idea about the properties or what's going on or what kind of interaction is happening using scanning tunneling spectroscopy. Regarding the field, see, in condensed matter, it has always been the case, the holy grail has always been room temperature superconductivity. There have been reports, there have been scandals, there have been all kinds of things related to room temperature superconductivity, but there is no room temperature superconductor yet. And all I want to specify, more than the open problems or the new questions, what I feel is there is a need to slow down and focus on the reproducibility of the results that we get in the lab. That, I think, is very important. Professor Ogle mentioned it in a slightly different context, but what I feel is that nowadays, when the rate of papers and the rate of newer results getting published is so high, it really is imperative, and the onus lies on each and every student as well as the PI to make sure that the results are really reproducible. In fact, you can check on YouTube, there was a conference on reproducibility in condensed matter physics, because there have been some recent, let's say, unsavory episodes regarding interpretation of results or claiming big things. So I think that is a much bigger question that we should look into and be conscientious about it. That's about it. Thank you so much.
Pardon me for my broken voice. Yeah. So our group, we study nano energy and quantum transport. It basically quantum confined materials. Okay. Earlier we used to say as nanomaterials. Now we say quantum confined. Okay, you have to put quantum on everything. The properties or the problem that we are interested is how defect, dielectric, and strain affect the properties of this material. Being a, most of the quantum confined material that we are interested are two-dimensional material. Two-dimensional means they are truly monolayer, okay, transition metal dichalcogenides. That comprises 80% of our work. Some of the quasi two-dimensional materials, maybe few layer of thicknesses. So material-wise, it's the TMDs, transition metal dichalcogenides. Aparna also mentioned on that. Then some perovskite material. Professor Ogle is here. So yeah, we learned a little bit of perovskite from him. And the perovskite also that we deal is kind of quasi two-dimensional perovskite. Then there are oxychalcogenides, which are high mobility material. So tomorrow I'll be sitting again with the quantum material and devices. Okay, there probably will tell a little bit about the high mobility materials. And recently we started working on tellurine. And just to be self-sufficient, our group, we do growth. Okay, so basically grow our material. We also these days kind of collaborating to get material from other places and do the exfoliation. But being in India, you need to know how to survive. So growing something is better. Then we fabricate device. So this is a kind of a crucial part for us. And that's why tomorrow we'll be telling a bit more in the quantum material and devices. Because we are supposed to do electronic transport property study. And for doing electronic transport, you need to have a device. Okay. If you're doing optical properties, then you can just, probe it without making a device, at least up to a good extent. But electronic transport requires a device. So we even do a little bit of research on how we can fabricate, device on some complex materials, okay, which do not survive in the conventional lithographic technique, and try to solve certain problems in those aspects as well. And after we study their electronic transport, or these days we are getting a little bit lazy, so we also started doing some optical measurements. So basically optoelectrical properties under various stimuli. That stimuli can be magnetic field, varying temperature, it can be a dielectric environment. Okay, we see how their property changes. And once we have understanding of how this, defect, dielectric, and strain affect this material, we want to see whether we can use them for some, practical applications. I mean, Professor Ogle started with, kind of near future applications. So we are looking at those kind of applications. And the applications that we are interested is basically for neuromorphic devices. One thing I can assure you that even, I don't know when the quantum computer will come, but the neuromorphic chips are already here. Okay. So we are interested in neuromorphic devices, mainly for brain-inspired computing, and also making ultra-sensitive sensor platform. We are not looking for a particular sensor. We are basically trying to provide a platform where you can detect various things. It can be a biological molecule, it can be a chemical, whatever is that. Okay, so basically we're trying to provide a platform, and we made some progress on that. And to support our research, we do a little bit of instrumentation. All the students, they have to take the pain of building something, even whether they like or not. And some recent results, like Pawan said that we should say some breakthroughs from our lab. I don't know whether the breakthrough does not, but at least student got either paper or a patent. Okay, so this one is, we developed a new growth promoter for this transition metal dichalcogenides, where you see here is a monolayer MOS2. It is conformally coated on a silicon, even highly structured material, where the radius of curvature is around 20 nanometer, and we are able to make the conformal coating even that high curvature. We got a patent on that growth promoter. Here we have a mixed dimensional van der Waals heterostructure. It's basically a 2D, 3D heterostructure, where we showed that by doing a dielectric engineering, we can improve the photoresponse by 3 orders of magnitude. Okay, here by applying strain, we are able to show that in a monolayer MOS2, you can activate and migrate the defect just by applying strain. Okay, in another work, here by applying strain at nanoscale, there the application of strain is kind of a little bit tricky. It's, there are pillars which are spacing of 52 nanometers center to center. Okay, you place a monolayer on top of them and you see how their property changes. And what we found that the dark exciton now gets brightened because of this application of strain at the nanoscale. You do hear a lot of about this twisted structure, Moire lattice, and here you can actually, by using this kind of substrate, we call it a substrate engineering, it's basically a part of dielectric engineering, you can just place one monolayer and you can probably mimic the same physics that you want to see by making a 1.1 degree twisted angle. Okay, so you don't need to really be so precise. You can just place the sample and the properties that we saw in this sample, they're still surviving after 5 years. So I think the reproducibility is there. Today, there are a lot of talk, and I think that is very important, reproducibility. We should not just be a paper mill. Even if you publish one paper in a year or maybe 2 years, but it should be reproducible, it should be useful. This one is again the application part, neuromorphic. So we tune the defect basically through defect engineering. We introduced defects in MOS2 and we found that their memoristic property increasing significantly compared to the pristine sample. Again, another example of defect engineering. So all these TMDs, they come with vacancies. Generally, if it is sulfur based, then the sulfur vacancies. If it is selenium or tellurium based, then the tellurium vacancies. Most of the time it is single vacancies, but what we found that if you can introduce double sulfur vacancy, means two sulfur vacancy together, then those samples gives very high mobility, and it's a mobility which is kind of really large. Okay, I mean large compared to these materials what you generally see. And recently we also found that now if you engineer a little bit of these materials, this is not a completely monolayer, it's basically started with a monolayer, but another layer is growing on top of it and there is a little bit of twist, so we call it a spiral geometry. And in this spiral sample, what we found that there is a phenomena known as bulk photovoltaic effect. I mean, you all probably know about a photovoltaic effect. Bulk photovoltaic effect doesn't require a PN junction or basically a heterojunction. Okay, the material itself has some asymmetry which helps them to generate photocurrent if you shine a light. Okay, the advantage is that it doesn't, there is no, Shockley-Coiser limit for the upper, there is an upper limit of the efficiency which is imposed by the Shockley-Coiser limit in case of PN junctions. And the origin of the photocurrent here is purely quantum mechanical thing, which I gave that responsibility to Srijit to teach me actually what is the fundamental physics behind it, but it comes from the shift current. And in another work, we found that there is a ferroelectricity present in perovskite, this two-dimensional perovskite. So it is probably the first report in this kind of systems. And also we found that if you scroll these monolayers, then it's kind of a layered structure, but because of the strain that you're applying, they are getting decoupled. So this is pretty much from our advanced materials part. And I'd just like to thank Pavan and the students for organizing. So we should give a big hand for the students and Pavan as well. Thank you.
Yeah, before taking questions from the audience, maybe we can just discuss with Professor Ogle here that in terms of advanced materials perspective, in the context of energy, in terms of advanced material perspective, in the context of energy, commercially speaking, silicon is still going strong. Everywhere you see on rooftop, those are silicon or at best polysilicon. So where do you think the actual connection will come? What is the challenges?
Yeah, so now in
what are the challenges?
Energy harvesting part is the solar cell, which is the key thing. But now it has gone far ahead with the hybrid perovskites. And the whole thing is many people have now decided that instead of competing with silicon, with different materials and engineering them differently, it is better to collaborate with silicon. So they are going to tandem systems, where silicon and on the top of that, they tune perovskites, hybrid perovskites, where you have, in fact, internal molecular motions also, as you know, in hybrid perovskites. And in the tandem systems, they have already reached around 31% efficiency. Silicon is normally around 23, 24 in the best case scenario, although technically up to 27. But now the limit they are trying to go to 41%, okay, by doing all this tandem and so on. So that is on that side. But the other important thing is the most challenging is batteries. Okay, because it is the most expensive proposition, and unless it is done on scale, and therefore I always say that in advanced materials, I have coined a word myself called pragmatic innovation. Okay, so what is important is affordability and scale are very critical. We can do all science, but unless it is, if you want to sort of unleash that on the societal scale, to be able to do that, you have to talk about affordability and scale. So people are trying to do all this research in energy using more and more component of earth-abundant materials. Okay, and 90% is composed of like silicon, iron, and so on and so forth. So I always tell students that suppose you write a good paper with some platinum or palladium or something, that is not going to scale and go to rural India and make applications of that. So even if they get 30% of that effect, what they get with these elements, okay, but it is 100,000 times less cost. Okay, that is a pragmatic aspect of innovation. So they can first see where you hit and then try to do something which is practically scalable over large. So advanced material is something which gives you that ability to try that, I think.
Okay. Prashanjit, in terms of advanced material heterostructures, they are important as we see from Professor Ogle, Atikur and everyone. But as far as I understand, you do these band structure calculations, and however in a heterostructure, band alignment is very crucial, and that plays a very crucial role in its device performance or functionality. So, however, I don't think there is a full-fledged theory on how to understand how the band alignment should be between two different materials. So can you throw some light on that?
Yeah, so the way it's usually done is you do a calculation for the heterostructure, and when you do the calculations, so depending on the strength of the interactions between, so there might be charge transfer from one side to another side. That results in the band bending. So you can get that from computing the band structure and looking into the density of states.
What determines whether the two band gap will align like that or align like that, or
That depends on many factors. One is, for example...
Are there any universal understanding of how the interface will...
No, so that depends on the interface and what chemical interactions takes place at the interface. Okay, so, but for example, the work functions of the two materials, that can be, I mean, how different they are, where they are placed, that can be some guiding point. And then if at the interface there is strong chemical interactions, then many things change. You have a very strong electric field also developed at the interface. So that will change things.
If I may ask...
Just make a comment, subsidiary comment, that this is an area where there is a big difference between theory and experiment. Okay, because experimentally you do UPS, you do all optical absorption and so on, and you get a particular band structure vis-a-vis the vacuum level and so on, and you put them together to see how the alignments are. But in theory now there is a lot of underestimation or overestimation of band gap, right? And how one is going to tackle that?
Yes, so this was one of the, I mean, if you remember, I listed some open challenges and questions. So the first one was to come up with a correct formulation of the exchange correlation functional. So all problems in DFT underestimation of band gap comes from the fact that we don't know the exact form of the exchange correlation functional. So all approximations goes in there. Now people have sort of tried to circumvent these problems to a certain extent, I mean, by using something called hybrid functionals or which is relatively cheaper compared to other more advanced methods, like you can do something called the GW approximation calculations. But those are very expensive. I mean, for a heterostructure with the facility which we have here, I cannot even imagine doing those calculations there. So that's the status right now.
Yeah, just in continuation of this thing, because we recently faced this issue. So, yeah, we don't work only in our lab. We do a lot of collaboration. I think Pawan and I probably published more than a dozen papers in collaboration. And in one of our recent papers, we have collaboration with Aparna, Prasanjit, Pawan. And there, I think this question is there that whether the GW calculation is possible or not. And then, Prasanjit has to write something that it is expensive and we cannot really do it. But yeah, fortunately, the paper is accepted. But yes, so we often, like I at least, maybe in a light mode, I tell Prasanjit that the hard work we are doing the experiment. Why you have difficulty in computing that? And he often comes and say that, no, I cannot do that. Okay. So yeah, it's not, only the experimental's life is, we have difficulties. Okay, they also have a lot of difficulties. And we are slowly learning that by doing collaboration. We are trying to share the pain. Yeah, I mean, Mukul is here also, okay. He is also one of my collaborators. And we also faced a lot of issue about this, band gap calculations when you place dielectric on top of it, and we do underestimate, how to really take into account of the actual change that is happening in experiment. I mean, Prasanjit said in the last point that there is a really gap between the length scale and the time scale, which I think is, is probably a big challenge, is an open question to solve every one of us, okay. That is very important.
See, in the context of this band gap, another problem is, I mean, you can see a lot of papers where people just use hybrid functionals and tell that, but it's not an ab initio functional, in the sense it depends on the parameter, that is how much of exact exchange you mix with the DFT correlation. So if you change that, your band gap change. So in principle, you can tune your band gap to any desirable value. So you lose the predictability, which is another strong point of computation. So that's the problem.
Okay, so Atikur, I just want to ask, you make a lot of these 2D material heterostructures and perovskite heterostructure. So it is still, meaning the Scotch tape method still is the best kind of material compared to CVD. So what, in your opinion, is the challenges for CVD growth of 2D materials?
Okay, this is indeed a very important point. And the reason I work with TMDs right now is primarily because TMDs you can grow very high quality using CVD. Okay, so during my first postdoc, I was working with graphene, all ultra-low quantum transport. And we all did with this Scotch tape sample. I also grow them using, chemical vapor deposition. Okay, they are fantastic. They grow over the entire substrate, so it's like a centimeter scale. But their Dirac point lies even beyond 100, volts. And I want them close to 1 volt or something. So they are not good for, at least the quantum transport applications. Okay, whereas then this, TMDs came, it has to come because graphene lacks band gap. Okay, so you cannot really, if you want to make a device, you cannot turn it off. Only thing you can make is analog devices with graphene. You cannot make a digital device, okay? Because for digital device, you need on and off state. Okay, graphene you cannot turn it off. The reason you cannot turn it off is beautiful, okay? It's, a lot of time it's primarily because of the quantum mechanical nature of it. Okay, even if you make a very sharp PN junction, depending on the sharpness, you can see the Klein tunneling. So you can even mimic Klein tunneling. We even did some work where we showed that the Klein tunneling happens if you make a very sharp PN junction in graphene. And there are some very beautiful work by Philip Kim. He was in Columbia during that time. Later he moved to Harvard. Okay, so the thing is that graphene, though the mobility is fantastic, everything is good, but in terms of the application, okay, there are a lot of bottlenecks. Okay, that's why probably even the graphene discovered at 2004, but still we don't see any real devices out of graphene. Whereas MOS2 or the TMDs, when it came, then people kind of jumped into it. And the reason is that one thing is that their property changes when you go to monolayer. So, the bulk sample, the photoluminescence or even the absorbance is pretty low because they have an indirect band gap. But the moment you make them monolayer, they're glowing like anything. Their PL is so high, you can even just observe them in bare eyes, especially WS2. You can easily see them. Okay, you don't need anything. Because in monolayer limit, they are direct band gap. Their band structure is changing. Yeah. Which might be very difficult for the theoreticians to really compute and so, but experimentally what we can see is that in the, yeah, now you can do it.
Okay, I think time for...
Yeah.
So he talked about mechanical exfoliation. There's another method which is liquid phase exfoliation. Which has been now shown, and a part of it I showed for boron, where we didn't make the sample, but we know the method and that it works. And there are other non-van der Waals. So see, van der Waals materials you can easily peel with scotch tape. Even those methods have been tried by the method of liquid phase exfoliation. But there are non-van der Waals materials also which can be exfoliated using liquid phase exfoliation. Of course, the sizes are small and all, but for fundamental studies, this is also a very good method that can be used.
Yeah, I think the main thing is the scalability, because if you want to, put it in applications, like all these TMDs and 2D materials, they are looking for, application. Okay, the reason this field got so much momentum is purely application driven. Okay, people want to make your, mobile faster, your computer faster. So the fundamental thing is the field effect transistor or the, FinFET, whatever is that, you have to make it smaller and smaller. So every time you hear that, okay, 5 nanometer technology node, you have a 5 nanometer node, 3 nanometer node, 2 nanometer node. People are trying to reduce the distance between the source and drain, and there the problem starts. Silicon is failing there. Okay, here comes the 2D material. It doesn't have a dangling bond. Okay, perfectly van der Waals, monolayer. You can turn them off. It doesn't have the problem of, pinching. All these problems it can solve. Advantage of TMD is that you can make them very high quality using chemical vapor deposition. You can grow them wafer scale. Okay, and their quality is as good as exfoliated. Even in our lab, we get the quality as good as exfoliated ones. Okay, so that is the advantage of TMDs. The reason is that why they are good, compared to exfoliated, because the parent crystal that you take when you exfoliate, that itself has sulfur vacancy. You cannot remove sulfur vacancy from there. Okay, and when you grow them on CVD, it also has the sulfur vacancy. Both are thermodynamically limited, and I think the thermodynamic limitation is not too bad compared to the bulk crystal to monolayer. Okay, in CVD.
I think we go for questions from the
It's open to.
audience.
Okay, Sachin.
Maybe we go
Yeah, professors are also students.
So the question is about, there was a recent Nobel Prize on AI finding the protein structure. And then there was a Google DeepMind which predicted some, tabulated materials, which is like, figure is like 10 times more materials than it could tabulate than what experimental lab or computational could do. I just want to, this is a very big question, I just want to know how is it impacting your research here, or how do you think like it is going to impact your research in terms of finding out materials which are really useful for, a lot of day-to-day activity or?
Yeah. So this field in batteries, there are these cathodes and anode material. This is the hottest area, and there is Gerban Seder in Berkeley. He's leading this effort on AI prediction, AI-based prediction of new materials and so on. So actually what they do is they sample lot of experimental data on one side, and also have a lot of theoretical, AI type of computational effort on the other, and they try to map it in some way and come out with a limited small number where the success rate for a particular property portfolio is substantial. And then they also have, see, the point is you may do a lot of computation very strongly, but it is important also to experimentally verify n number of materials in those experimental labs. So what is going on is robotic, processing of many of those chemicals in synthesis. Device making is coming. So, for example, electrolytes in batteries, you can predict something, but then the robots will do it extremely fast, mix and do these materials, which we normally in chemistry lab may do some trial, error and intuition with your experience and so on. But with this, these robots will directly couple with this AI ML type of discoveries and do that. So this is one of the biggest things is happening in energy materials, particularly batteries. And I think there is, even in our lab in TCG Crest, there are 2 people working on this. And there are different ways of doing it. In fact, some people, what they try to do is look at some theoretical complete analysis based on the property of that material, generate those, and around that have a Gaussian distribution of different properties and try to design those materials. From that, enhance some kind of a predictability by an overlap and so on, and try to come up with some new material discovery. So this is something which is making inroads into energy research in particular, and in broad material research in a very big way, I think.
Yeah, so yes, not only for batteries, but also people are coming up with catalysts. They are predicting new catalysts. But the problem which I personally think there are 2 issues, at least in the area of material science. One is the volume of data that is quite limited. So what is necessary is coming up with new algorithms which can work and predict with small volume of data. And secondly, consistency in the data, even within the theoretical calculations also, if you restrict yourself, different people do different level of accuracy calculations. So that might make your model completely go wrong. So that, and then if you add experimental ones, then there are more problems. So these are the problems. And another thing which I find, which was a strong deterrent for me for not to go into machine learning in the early days was people were using them just to, as I said, develop structure-property relationships. For example, say I have a material A, I know its electronegativity or some property which can be very easily measurable. Can I have an equation, it may be 1 or it may be 10 properties, but can I have an equation which can give me the band gap, suppose, as a function of those properties. So people will have a lot of data and then they fit it and they will get some relationship. For example, the electronegativity goes to the power of minus 0.78652. Now what do I do with that equation, right? So I don't understand anything apart from saying that, okay, if this has this, then this is the band gap you get. So the physics or the chemistry, that picture is getting lost in that process. But what now people over the last, say, 10 years or so have been like people like Carparnello and then his group members. And then now there are a lot of other like Kasser, Gabbiani, or other people. They are coming up with this machine learning interatomic potentials. So that is coming up pretty nicely. It has its own challenges and difficulties till now, but that is something which I think is more useful and can help us to give a microscopic picture, because that will speed up calculations quite a lot.
So you are waiting for quantum computer?
No, quantum computer, I don't think in our lifetime we will be able to do material simulations using quantum computer. I don't think it's going that way.
Initially, that's the main goal, right?
Yeah, but it's not going that way, I think.
Yeah, we are at the very surface scratching of this whole field. It is very deep, and a large number of scientists are now going very strongly into it. And I think an organization like Google with supercomputing power can only deliver on some of the things which can be practical at the moment. So small universities or something will not be able to deliver on that scale at this time. But they will probably, once the supercomputers proliferate very strongly, the power, then I think you will get a lot of tangible results soon, I think.
Any questions from the audience?
Umakant.
Yeah, Prasanjit, you mentioned that one of the problems in your DFT, Mukul is looking at me. Yeah. So was that it's hard to incorporate correlations of the electrons, right? But then you also said at some point that you could put it, no, I mean, the community could put it by hand or something empirically and then match the experimental results.
No. That is, okay. So that is this for this hybrid functionals.
Okay.
Where basically, see,
No.
the exchange correlation, let me finish.
No, I have my question is not over, so this
Okay.
is halfway through. So you said you do something and put that by hand or empirically?
No, we
whatever.
don't put that by hand. We mix the exchange and the correlation empirically.
So once you do that for bulk, say, I don't know, some material which is in bulk, now if I, like Atikur said, you deposit that material on some substrate and then the property gets modified. So once you put that in bulk, can you use the same functionals or whatever for that particular system and get it, or you need to again change this
So
correlation?
that's where my objection is. People in the community use the same mixing, irrespective of where you go. But that's where, I mean, all the empirical aspect is coming into the picture. It might change, and these calculations are expensive. But now what people are doing is sort of trying to evaluate it in a self-consistent way, so that how much you need to mix of the exchange and the correlation part, that is no more empirical. But still a very expensive thing to do.
Small comment that I think experimentalists are looking right now for these kinds of calculations more as a guidance, in terms of charge transfer and so on, not a quantitative comparison with experimental results. So the predictions, if they are in the reasonable ballpark to see, then the experiment can take over and do something. So if they say that, okay, it is like, okay, you go to this area and then find something your way there. So at least that much predictability, if it is afforded by these computational calculations, that is already quite a success. And then the experimentalists tune down to nail it actually in that way. There was some question, I think.
Question from student.
My question to Prasanjit, when I see like material science, people are choosing some like random sample or material like perovskite for some properties, so Hafer-Schiller for some properties. How you go about choosing some particular material for defined properties? Because it seems for me like it's just random.
No, I don't think it's really random, whether you, do it in a lab, okay, whether you are experimentally synthesizing it. There is some logical reasoning or logical thought behind that. So it's not completely random. So having said that, sometimes people also try to mix and match also. And I think that's where we can, as a computational person, we can come into the picture. We can help in a more rational way of making those materials, or at least identifying the interesting candidates for a particular target applications.
Yeah, if I may add something there, is in this case actually these excitons may turn out to be really fruitful, because excitons can show a variety of property based on how you put into what kind of material or what kind of material structures. For example, 2D materials, the binding energy is so high, these excitons and even their collective property survives at room temperatures and beyond. So, and specifically, these excitons can be controlled to dance in unison. And whence they can dance in unison, many collective phenomena like Bose-Einstein condensation, even the BCS superconductivity, one can think of experiencing or experimenting or kind of realizing in materials which are having these excitons. So if you can think that excitons, electron hole pairs are created in semiconductors. Semiconductors, by their definitions, conductivity is much smaller than the metal, in between, half in between the metal and insulator. But these excitons within a semiconductor material can be driven to a BCS superconductivity and display superconducting behavior. So it's really counterintuitive, and you can think of physics-wise designing certain exotonic materials to observe or to see if these properties are really can be achievable or not. There are certainly some papers. We are also doing some work on that. Unfortunately, the students have an exam tomorrow and they could not present it.
I will just make a comment that this idea of complete randomness and people choosing something, take that cloth and measure something, it doesn't happen that way. Scientists are not that stupid, okay? Don't think that way. You know, many people are quite intelligent, they are doing this job seriously, so do not demean them by making such a stupid comment, okay? For example, I will tell you, some scientists come with conviction, intuition, okay, over time they have worked. I will give you an example of Mueller, who won the Nobel Prize for high TC superconductivity. I had met him in '89 in Maryland, and he was working on superconductivity for a long time, thinking about oxides. Why oxides are having strong phonon structures, ionically bonded, why it is not showing high temperature superconductivity. People are getting Nb3, germanium and so on, 27 Kelvin. He was trying to see why oxides are not. And that oxide we tried was strontium titanate, and 0.1 degree Kelvin was the transition temperature. But he didn't give up. For 7 more years, he tried oxides and he finally got YBCO and the Nobel Prize. So people work with scientific intuition. We have to respect it. So they are not choosing some material, take a stone and measure some conductivity. It's not like that, okay? I have to tell it emphatically because people have this problem.
Yeah, there is one.
My question is to Dr. Atikur Rahman. So you talked about neuromorphic chips, and especially in the context of a superfast classification of handwritten digit. So, like, what are the advantages of these neuromorphic chips compared to the usual one, and what kind of advantages you saw in that particular, like, you know, example that you saw?
I think, so the present day computer, okay, it has a memory and storage. Okay, that's called the von Neumann architecture. All that you use is based on von Neumann architecture. And the problem is that, okay, you need to shuttle the information from storage to memory, okay, to perform a job. But our brain doesn't do that. It doesn't have a separate storage and memory, okay. It, it performs the calculation right there where you can say the memory is, okay. So, processor or storage, okay. So both the processor and the memory are staying at the same place, okay. That is the neuromorphic architecture, okay, how your basically synapse works. So that solves the problem of storage, power consumption, okay. There's, forget about the big data centers. Just look at our simple Param Brahma. Just to cool that, we have a separate cooler, okay, outside. You probably all found that. Brain works only on 10 watt energy, okay, and it probably, billion times stronger than the Param Brahma. So the energy requirement for, say, per bit or something is much lower because you don't need to shuttle the information from your processor to your storage, okay. So that's the biggest advantage in neuromorphic computing. So all these AI and other things, they are highly, packed with data. It's like, high volume of data. And if you can perform them, using the neuromorphic architecture, then it will be, energetically it will be very efficient, okay. So that is one biggest advantage.
Yes, I have a last question from Professor Ogle. So from Professor Ogle, as people are going to merge particle A, B, C, like this kind of different materials, and out of that they are going to get some emergent phenomena, right? And if there is no theory behind that, so how the scientist should think that the emerging phenomena is going to explain, right? At that point, how some scientist should stay at that particular question. So could you comment on that? I mean, if there is no theory and somebody is going to...
No. See, when people do, earlier in chemistry,
Yes.
you had alchemy. So the trial and error used to be for several hundred years. People have done from zinc battery in Egypt and so on. From that time on, people had done trial and error. Nobody was born with a theory, right? Yeah. People were doing experiments only earlier. Now, as models kept developing, there was an aid in that particular process, okay? Now, when slowly the electronic bonding chemistry was born, and chemistry is very central to material science, okay? Now, physics is something which measures all those properties. The two things go hand in hand, okay? So, as they say, that photoelectric effect existed before Einstein explained it, and they were using already photoelectric effect, yes. Right? So that was there, and he explained and got Nobel Prize for photoelectric effect, not for relativity.
Yes.
Okay, so all these things happen. So it is a kind of it is more like a game, you know, like a hockey game, yes. Where somebody sees something, it gives a pass to somebody, he passes somewhere, and finally the goal is something which is very important. So theory and experiment go hand in hand, try to help each other in one way or the other. But chemists have a kind of, because I worked a lot with chemists now in material science area, you know, they have developed an intuition of different kind, okay, with their orbital structures, their orbital strength. So for example, F electron, the orbital is longer, you know, p orbital, how is the shape of the orbital. So they already know which things will be able to put together to generate a particular compound. So I think there is a lot of intuition and experience of people in putting together materials of interest. I think that's why, and the theory then gives aid to further understanding of physical properties in particular, which can be measured separately. So it is a very, very kind of, you know, responsible game. It is not randomly being done, okay?
Shiva,
just to add to, on a lighter note, collaborate with a theoretician.
Shiva has...
You almost said like walk like an Egyptian.
My question is, besides computing or computational approaches and machine learning, AI, these really push these advanced function materials, predicting new ones, discovering new ones. Also on the side of instrumentation, the new discoveries that are made. For instance, Aparna here is using scanning tunneling microscope for 2D materials and things. So in that spirit, what are the new advances on the side of instrumentation which is sort of guiding this field also is my question, because almost every field is pushed very strongly by new development of instruments.
So I think the most critical development from my standpoint is in operando studies, okay, in systems. Like if you take, when a phenomenon is happening, can you in real time see what is happening inside that device? And techniques which are developed for that, okay. Now for example, if you take a battery, you cannot do X-ray photoelectron spectroscopy because your X-rays will not go in and electrons will not come out. X-rays will go in, but electrons will not come out. And so how can you do X-ray photoelectron spectroscopy when lithium has gone from one end to the other? Okay, can you use synchrotron for something? Can you use, all these kinds of things are coming up. So the hottest topics that you will see, NMR, okay, and solid state NMR, then X-ray tomography, you see inside, and try to get imaging of how dendrites are formed and so on. So I personally feel in operando studies using high techniques of this kind to see the phenomenon as it is happening is something which is a real advance. And in the last about 5 years' time, you see many papers and people have made big names for themselves just by focusing on in operando studies. That is from my point of view, but there would be other answers, I think.
Especially for materials, now transmission electron microscopy and the advances in transmission electron microscopy where you have selected area diffraction patterns. So these are very much helpful, especially for these advanced materials. So where, though TM has been there for a long time, the advances in TM itself have been very useful of late.
I just want to add just one answer to his question.
No, Shovik, because she mentioned TM, I just want to add one point.
Okay.
Sure. So I mean, usually TEM people do at ultra high vacuum, low temperatures and all. But now people are doing TEM to study how reactions, okay, at normal temperatures and stuff, where people can see, I mean, the molecules oscillating, how they're breaking. So just put it.
I remember when your PhD supervisor, Dharmadhikari sir, arranged a conference on electron microscopy in Pune University, and I attended that. And one of my questions to that time panel members were why we are not using X-ray. It turns out that of late, and they said, go ahead and try to develop it and design it, you will get a Nobel Prize. It turns out that Zeiss recently, Carl Zeiss, recently came up with an X-ray microscope whose resolution actually goes to the level of electron microscope.
Single peptide.
Yeah, yeah.
I think,
Not in the
this
nanometer, but micrometer.
entire, nano physics, it started because of the development of instruments. Okay. Because the physics that they're doing is kind of very simple. Particle in a box. Okay. Just simple tunneling. Okay. All you see, they are not, that like new physics that was discovered maybe 2 years back or something. It started like that. Okay. But yes, it started with, some particle in a box problem. But now, with this twisted structure and other thing, there are new phenomena where no theory exists. Theoreticians do exist, but the theories still, don't exist. Okay. So, yeah, that's how the field moves. Sometimes, theoretical predictions were there. You need to realize it, and that is definitely possible because of the instrument. Sometimes you come up with some experimental, observations where the theory were not there. Just Professor Ogle said high TC superconductor. When the Nobel Prize is given, there is no theory. We still don't have a proper understanding of how it works. Okay, people are looking for high conducting material to get superconductivity. Why someone will look on some oxide material which is supposed to be insulating on superconductivity? Okay.
Or a semiconductor.
Yeah, exactly. So, sometimes someone is a bit ahead, theory is a bit ahead, sometimes experiment is a bit ahead. Okay. But yeah, they do collaborate. Okay.
So theory has picked up over the last few decades, I think, with the advancement of supercomputers.
Okay. So
last short question for Professor Ogle.
Okay. Quick,
Yeah. So
it's
this
already
battery development, you talked about earth abundant materials, and I have seen that there has been a lot of work going on since many decades on using sodium, replacing sodium, lithium with sodium for batteries. What's the current status on that?
So it is actually sodium is, in fact, I'm very happy to say that we had a wonderful project with this KPIT company at IISER. And the first lab to market product will now come up. One company has actually bought that technology now. It's called Trentar Technologies Limited. And for the product which was developed in collaboration with IISER on sodium battery will come into market in some area. Worldwide, sodium technology is picking up very rapidly. Although sodium has lower gravimetric capacity, volumetric capacity, there are niche applications for it. Maybe two-wheeler sodium won't be there because it will be heavier battery slightly. But trucks, heavy vehicles, ground station, charging station, it has tremendous advantage. Sodium battery can also be discharged fully. Lithium battery cannot be discharged because if it discharged fully, it produces dendrites. Okay, and also, so while traveling with that battery, there is a limitation on how, there are various problems. So sodium also is abundant even in India. We can get sodium and purify it. But lithium is only in Chile and Argentina and somewhere. So, and China has already bought those hills and mines and so on. So there is huge problem without recycling. So this field is very, very fragile now, and it is turbulent, lot of activity, and sodium will be picking up, I think. Yeah.
Okay, so let's give a big round of applause to the panel. And also an applause for yourself for staying back into the evening session. One more important point, this is actually, there's a lot of activity going on. I have to also mention that some of our colleagues are traveling, and many of them actually are also condensed matter physicists, Surjit, Ashna, Sunil Nair, Ashish Arora, and a few of the other colleagues also in astrophysics, for example, Ramana wasn't around. So there are many other people who could not make it because they were traveling. So their students actually are presenting posters. Since they are not here, they are not able to actually attend the panel sessions. Do actually visit their posters and interact with their students. So you'll also get a flavor of advanced materials. Okay, so we end the session for this evening. And
thanks to you.
Yeah, the advanced materials. There's also a quantum materials which is coming up. But tomorrow morning, 9:30 a.m., we regroup here with particle physics.